So mass is relative. We all know that. Or do we? Well, we all know about the law of conservation of energy, right? According to which, the amount of energy with which the universe was born during Big Bang is the amount of energy we will always have. In short, energy can neither be created nor destroyed. It only changes forms. Well, yeah, it's correct, mostly. Now, for instance, let's say you are standing on the ground observing a car moving. For you, the car is in motion. And well, motion again is relative. So for someone moving with the same speed as that of the car in the same direction would observe that the car is not moving. Now, if I ask you, the observer, standing on the ground, what is its kinetic energy? You say half times mass of the car times velocity squared. Well, you would be right, but if I ask someone moving with the same velocity as the car with the same speed in the same direction, what is the kinetic energy possessed by the car? He, being utterly stupid, would start calculating. Half times the mass of the car times the velocity squared. But the velocity is 0, so yes, the kinetic energy of the car is 0. But wait, hold on a second. How did that happen? You know for sure that the car has the amount of kinetic energy. And this gets a bit weirder. If we also consider the energy mass equivalence, which means that we can consider energy and mass alike, what would that leave us with? The mass of the car is different for you and the other observer. Now, who is right? Well, turns out you both are. And this is where we enter the realm of relativistic mass. Now, I guarantee that this is not as complex as it sounds, and you will not regret sticking till the end of the video. So in the above scenario, even though the difference in energy seems like a lot, it's actually not so much considering the total amount of energies in the body. The total energy of the body comes from two places, from the kinetic energy of the body and the actual rest mass of the body. Let me explain. The rest mass and the relativistic mass of a body are often confused under just mass. Relativistic mass is an old concept, but it is actually quite helpful in understanding these things. Well, firstly, rest mass is the energy inside a body due to its substance, its fundamental particles and the energies of bonds between them. And this can be obtained by the energy mass equivalence is equal to mc square. Relativistic mass, on the other hand, is the total energy contained in a body, which means the energy due to rest mass plus the kinetic energy. Well, if some of you have heard of relativistic mass, you must also have heard that it only comes into play when an object is accelerated to high velocities, velocities which are comparable to the speed of light. Now this can be explained by the above example. When we calculate the total energy of the body, which is relativistic mass, we should add the rest mass of the body, and the energy due to it can be calculated by the energy mass equivalence is equal to mc square. Now when we multiply, let's say, the mass of a body having 100 kilos times the velocity of light, the energy is quite big. Now at small velocities, the energy due to kinetic energy of the body forms a very small chunk of the total energy of the body. So relativistic mass is almost equal to the mass, and we cannot even notice a difference. However, when objects reach high velocities, velocities which are comparable to the speed of light, the kinetic energy of the body starts forming a major chunk of the total energy. And moreover, I need to remind you that E is equal to mc square is only half the story. This is because it only accounts for the rest mass. Well, in reality, there's indeed a momentum component in the equation which actually accounts for all the energy in the body. Now, if some of you want the equation, I must have put it up somewhere here or here, just. So, our takeaway from this, energy is dependent upon the frame of reference. It is indeed conserved throughout the universe, but you cannot just observe different frames of reference and expect the energies to add up in the same way. Mass is absolute, but relativistic mass isn't. This is because the total energy of the body depends upon the frame of reference. Now you see, relativistic mass is an old concept. It was used to explain the change in momentum of bodies moving at really high velocities. Momentum is always equal to gamma times the rest mass of the body times its velocity. And at slower speeds, gamma, which is actually 1 divided by the whole root of 1 minus v square by c square, is near 1. And thus, we need not account for that in our equation. But at greater speeds, gamma starts to make a difference, and we simply write gamma times rest mass as relativistic mass, which turns out that it is the total energy of the body. So even in our previous example of the car, mass is conserved, but it is different for a different frame of reference. Well, if this helps, energy is conserved, but it is not invariant. Conserved quantities are those quantities which remain constant over time, which means that the amount of energy with which the universe was born at the time of Big Bang stays constant no matter when we observe it. Whereas an invariant quantity never changes with the frame of reference. A good example would be the speed of light. The speed of light never changes, and that is around what the entire theory of relativity is based. Special relativity is based. So, for a more technical example, let's say you start observing a body at t equals to 0. The energy would stay constant no matter at t equals to what you observe it. Now, if you change the frame of reference, the energy might change. But for an invariant quantity such as speed of light, it wouldn't change. So apparently, energy is conserved, but it's not invariant. So, different observers in different frames of reference might record different energies for the universe. But over time, the energies for their frames of reference will never change. Well, so I know that this is a lot to grasp, so feel free to rewind the video, watch it again. More watch time is always appreciated. And if you made it this far in the video, I'm guessing you like it. So, thanks for watching. Like, you know what to do next. I wouldn't say that.